All right, folks. My apologies for the not too great lecture yesterday. So I'm trying to try to go through a lot of that, and I'll probably go through it reasonably fast. So please stay with me. If you have any questions, just ask. So here was the problem, right? I'm going to revisit many of the topics we did. We were trying to train neural networks to be generative models. So from a large collection of images of faces, we want to train a network to learn to generate a new portrait. Or maybe from a collection of landscapes, we want to train a network to generate new landscape pictures. So in each case, we want to learn the distribution of the data, in this case, images of landscapes, and know how to draw a new sample from this distribution so that when you draw this new sample, it also looks like a landscape. So we've seen how to use neural networks as recurrent networks, classifiers, and regressors. Now we're speaking of how to use neural networks as generative models to model the distribution of any data so that we can draw samples from it. Now, what is a generative model? As we saw, this is a model for the probability distribution of a data. The computational equivalent is that we have some magic box, and it can be excited with some random seed, and it's going to generate data with that looks similar, statistically similar to whatever this magic box has been trained to emulate. So, but generative models can also be thought of as distributions. So we've seen parametric distributions. So for example, we've seen the probability with the category probability mass function, like the roll of a die or a Gaussian distribution. These two are generative models. We also saw that the way you would want to learn a generative model is that you'd be given some observed data X, and you choose a parametric model for the distribution of the data. So P of X semicolon theta is the parametric model, where theta represents the parameters of the model. And we want to estimate theta so that this P of X theta best fits the distributions of X. And for instance, if we had a collection of outcomes of the roll of a die, which had this histogram, then we want to learn the probabilities for the faces of the die that could best explain this histogram. Or if we had a collection of data that was histogram looked like this bell shape, and we decided to model it as a Gaussian, then we wanted to estimate the parameters of the Gaussian that best explained this data. Now, do you guys remember what the principle was behind how we estimated these parameters? Anyone? Does anyone remember that? Hello, anyone here? Yeah, so it was the maximum likelihood estimate, and the MLE was based on the assumption that the world is a boring place, that the data that you're seeing are very typical of the process that you're trying to model. And so, in fact, we're going to pick the distribution or the distribution parameters for which the probability that assign the highest probability to your data. And so we saw a couple of instances of this. For example, when we were trying to model, learn the distribution of a category, the parameters of a category distribution that best explained a histogram, then the log probability of the data was given by this formula over here. It's the sum over all possible outcomes of the number of times the outcome was observed times the log of the probability of that outcome. If you maximize this with respect to the probabilities of the outcomes, you end up with a familiar ratio formula for these probabilities. Similarly, for the Gaussian, if you had a collection of data and if you computed the log Gaussians for all of this data, this would be a function of the mean and the variance of the Gaussian. If you maximize this log likelihood with respect to the mean and the variance, we ended up with well-known formulae for mean and variance. So this we saw. We also saw that in some cases, the data provided may be incomplete, may be insufficient to write out a complete log probability because the data could have missing components or because of the structure of the model. So in this instance, where the data have missing components, we saw an example of trying to learn a Gaussian distribution from a collection of vectors where some components were missing. So here, these are the data that you see. These are the observed vectors, and these components are missing. The complete data, of course, include the observed and missing components, but we don't actually have the complete data. Now, when you use the maximum likelihood principle, we want to maximize the likelihood of observed data. So, because that's all you really have. And so this is the sum over all observations of the log of the probability of the specific components that you have observed in that vector. Unfortunately, as we saw, Gaussians are not defined on incomplete vectors, they're defined on complete vectors. And a complete vector is basically the combination of the observed and missing components. And so the way we would get the probability of just the observed components was by marginalizing out the missing components, by integrating them out of the distribution. And so the log probability of the training data is going to, which only considers the log of the probabilities of the observed components, has an integral inside the log, which is, and so trying to maximize this guy with respect to the parameters of the Gaussian is not going to be easy because you have the log of an integral that must be maximized. Or we saw this other case where we had a Gaussian mixture model. So here the generative model is this. You're given a collection of Gaussians, and in each draw, the process first selects a Gaussian and then generates an observation from the Gaussian. And so what you finally get to observe are just these observations. If you look at the distribution of the final observations output by this box, it's going to be a convex combination of many Gaussians and can have an arbitrarily complex shape. And so we want to learn the parameters of these Gaussian that best model the distribution of this observation, which can have these observations, and where the distribution can have a fairly complex shape. But then, if you think about this from the perspective of the generating process, then in order to generate any observation, the process actually draws two variables. First, it selects a Gaussian, then it draws a vector from that Gaussian. So the probability of a specific generation is the joint probability of selecting a particular Gaussian and that Gaussian generating the observation that you just saw. So it's going to be the probability of selecting the Gaussian times the probability of the observation as computed by the Gaussian. And so the overall probability of any observation has to sum over all Gaussians. You could have generated this observation by selecting this Gaussian and this Gaussian generating the observation, or by selecting this Gaussian and then this Gaussian generating the observation, and so on. So you have to sum the product of the probability of selecting the Gaussian and the Gaussian generating that observation over all of the Gaussians. Now, so if you want to learn the distribution, you need to know everything that the generating process actually drew, all the steps that it went through in order to generate an observation. In other words, with every vector, you would also need to know which Gaussian was used to generate that vector. And if you had that, you could segregate out the vectors drawn from each of the Gaussians, and then you could estimate the parameters of those Gaussians. So this was easy. Our problem was that we actually only get to see the observations. We don't see the Gaussians the observations were drawn from. So what we need is the union of the observation and the Gaussian what we get are just the observations themselves. And so when we try to maximize the log likelihood of what we have observed, we have to, we'll be estimating the parameters of all of the Gaussians to maximize this term here, which is the log likelihood of the entire data that we have observed, except that we have only observed the vectors. We don't know which Gaussians they came from. So the Gaussians have to be marginalized out. And so the maximum likelihood estimate ends up with the summation term inside the log, which is hard to maximize. And so we had this general form of the problem where you had some missing data or variables. And this results in an estimate of this form where you have a summation or an integral inside a log where the inner term marginalizes out the components of the variables that you did not observe. And this form of function is very hard to optimize. And so we need some kind of a simple, tractable approach to dealing with these problems. So do we remember all of this? You guys are here, so I'd like to see some raised hands to make sure that all of this is recalled. So, okay. So guys, please stay with me, respond, because otherwise it will slow us down, right? So the way we did this, and this is where I believe I began losing you. We can rewrite log of P of O, which is log of the sum over all the missing variables of the joint or the hidden variables of the joint probability of H and O as sum over H, QH, PHO over Q of H, where Q of H is some distribution over H. So once we write this, we used the concavity of the logarithm function to show that the log of a convex combination of terms is an upper bound on the convex combination of the log of the terms. So this term to the right, which is the weighted combination of log of PH over QH, where the weights are QH themselves, this term to the right is a lower bound on log of P of H, comma O. So this term, the term to the right, is a variational lower bound on log P of, also called an evidence lower bound. So do you guys remember this? Any doubts about this? Over here. So do you remember this, or were there any doubts? If you remember this, please raise your hands. Okay, so no doubts, right? And so I've explicitly shown that this P of O is actually a function of the parameters. I put the theta on either side. Now, how did this work? This term to the right is a lower bound on log P of O. It's going to be log P of O is some function of theta. If you change the parameters, the probability changes. And so the lower bound is going to be some function below it. And if it's a tight lower bound, then when you maximize the lower bound, you hope to also maximize F. And so this was what we were trying to tee off of.
Professor, there's a question. What does variation mean?
So variational lower bound, this is just a terminology. This is called a variational approximation. This is literally called a variational lower bound. It's the calculus of variations. It's terminology as far as we are concerned, right? That's why we drop the term variation and often use the term evidence lower bound, ELBO. And we'll see why the evidence comes in, right? So you're sort of comfortable with the idea that it's a lower bound. And so log of P of O is lower bounded by this term. And so how can we make this lower bound tight? We can make this lower bound tight by choosing the Q of H so that it becomes tight. We want it to be as tight as possible, right? And so we had a two-step solution where we first made the lower bound tight by choosing the appropriate Q of H, and then maximize this term with respect to theta with this tight lower bound, and then it repeated the process. Now, how do we find the Q of H that makes the lower bound tight? It's very simple. We know that this term to the right is upper bounded by log of P of O, right? This thing over here. So if I maximize this, what is the largest value this guy can take? Anyone? If I maximize this, what is the largest value it can take? Log of P of O, right? And so I can maximize it. So what I can do is literally use, take the derivative with respect to the Q of H's with the constraint that they're all positive and sum to 1. And then I can solve for Q of H. In other situations, that's unconstrained. I may have constraints on Q of H, where Q of H is specifically modeled by a neural network or something else. In that case, you can't just you can't take derivatives and equate to 0, but you can still maximize this by using some kind of backprop on Q of H to maximize this term. Regardless, we can find the Q of H that maximizes this lower bound. And then once we do that, so if we didn't have constraints, we just maximize this with respect to Q of H, unconstrained. What we would find is that the Q of H that maximizes this term is the conditional probability of H given O using the current value of theta. So here's what we're going to do. For this optimization problem, I'm going to estimate the Q of H to maximize this guy, and then fix Q of H and maximize this term to the right? So let's choose a Q of H. And based on this knowledge that if you explicitly maximize this, you're going to find Q of H is the best Q of H is P of H given O. If theta prime, so again, this is using the current estimate of theta over here. If theta prime is the current estimate of theta, I'm just going to set Q of H to P of H given O, computed using theta prime as the parameters. So now for the second step, I fix Q of H and maximize the right hand side. So if I fix Q of H, Q is given by P of H given O with theta prime as the parameter. So this is going to be the sum over all H of P of H given O with theta prime as parameter of log of the joint of H and P of H and O divided by P of H given O with theta prime as the parameter. This here is Q of H. This term here too is the Q of H. So this is this bit, is the equation, the surface equation kind of clear, or is there any doubt over here? Any confusions? Can we just say Q of H is? No. So I'll tell you why. Okay. So this, yeah. So let me see tell you why I chose this particular one, but we can generalize, okay? So observe that now this term to the right actually has two instances of theta. One is theta prime that was used to obtain Q of H, right? The other is theta, which occurs inside this guy. So this lower bound is a function of theta prime and theta. Is this making sense, guys? The second term? So I'd like to see like a few hands raised, right? So we also know that because it's a lower bound, log of P of O is always an upper bound on J theta theta prime. I'm going to call this an auxiliary function. It's this term over here, which is the evidence lower bound, right? Now we can see that theta prime is just some parameter that I use to decide Q, but it's actually a function of theta. Do you see this too? If I look at it from the perspective of, say, this step. Over here, Q of H is fixed. So theta prime is just a parameter. It's actually a function of theta. Is this making sense? Right. And specifically, when these two thetas are the same, then you can then the right hand side simply becomes log of P of O. So how is that? Let me see this. This has two term instance, theta 1 and theta 2, right? If both of them are the same, j theta theta, then it's P of H given O with theta as parameter, log of P of H comma O divided by P of H given O. And P of H comma O divided by P of H given O is just P of O, right? So this entire thing becomes P of H given O log P of O. And log P of O is not a parameter function of H, so it can come out. So this is the summation over H, P of H, and the sum of any probability distribution is 1. So this is just, wait, what happened here? So this is just log of P of O. So do you see how j theta theta is log of P of O? Guys? Okay. So how does this work for us? Here's what we will do, right? This gives us our EM algorithm. I'm going to define j theta theta prime as this term over here, where Q of H is P of H given O with theta prime as parameter. And inside you have log of P of HO with theta as parameter. We know that P of O, log P of O upper bounds j theta theta prime. And we also know that log P of O theta equals j theta theta prime. So using these, we end up with a nice iterative algorithm. I can use the current estimate of theta over here and maximize j with respect to the theta here and make that my next estimate. And it will keep increasing my log likelihood. If you don't believe me, I'm going to show this pictorially. So let's say I start off with an initial value theta 0. I stick in that theta 0 out here, all right? So when I stick in the theta 0 out here, I'm going to get a j theta theta 0, which is a function of theta, right? And this is a strict lower bound on the actual log probability, which is a function of theta. So is that making sense to you guys? Over here. So, but then when theta becomes exactly equal to theta 0, you're going to get this lower bound being equal to log of P of O theta 0, right? That's what we just saw. So the blue curve is going to touch the red curve when theta equals theta 0. But then I can vary this theta. And then if I vary this theta, I can find the specific theta where j theta theta 0 is maximum, right? And I know from the property of lower bounds that at this value, if I call this theta 1, j theta 1 theta 0 is guaranteed to be less than P of O theta 1, right? You guys get this? So what does this mean? As a result of this, if I maximize this j function at the theta where j is maximized, the log of P of O2 is going to be such that the log of P of O here is guaranteed to be greater than the log of P of O over here. Do you see how that happens? Is this clear, guys, how this is happening? I'd like to see a few more hands raised, right? So this is our very simple trick. Here's what I'm going to do. I'm going to start off with a theta 0, plug in the theta 0 to the right over here and create one j function. Then I maximize the j function. That's going to give me this, right? Then that gives me a theta 1, and this new theta 1 gives me, has, at this new theta 1, the log likelihood of the data is greater than at theta 0. So now I'm going to create a new j function with theta 1 on the right-hand side. And so the new j function is going to touch my log likelihood function over here. And then I maximize this guy. And when I maximize this guy, I'm going to get my theta 2. And I'm again using the same property. I know that the log likelihood of my data using theta 2 as a parameter is greater than the log likelihood with theta 1 as a parameter. So I've increased the log likelihood. Now I'm going to create yet another j function with theta 2 as my parameter and maximize this guy. And I keep repeating this until I find a j function, I find a maximum where the maximum of the j and the maximum of the p are the same. So there's not, the algorithm cannot move any further. But this is a guaranteed, the iterations are guaranteed to always increase, or at least not decrease, the log likelihood of the data. And you're right, Eric, this can go into a local minimum. This is much like gradient descent. So this is the EM algorithm. Did this make sense to you guys? Here's the critical question. Did this make more sense than 2 days ago? Or yesterday? I'd like to see some hands raised. If it didn't, I'd like someone to state that it didn't. Okay. So you can see how this works, right? How the math works. And that's your iterative algorithm. Anyway, so skip this. So this was training by maximizing a variational lower bound on the log likelihood of the data, right? That's so much math. But what does it really do, right? So let's take a look. And this is where I believe I really lost you. So consider this case where the data have missing components, right? What EM really does is to complete the data. So we have this incomplete data where you only have partial components. So now consider one single vector. This single vector has a missing component, right? So I'm going to try to fill it up somehow. So let me ask you a question. Suppose I have a data which has, this is very annoying. I'm going to, suppose I have a data which can have, say, why won't this write? Okay. Suppose I have a data of this kind where it takes only these 4 values. For whatever reason, it only takes these 4 values, okay? And let's say the probabilities over here are 0.1. This is 0.1. This is 0.3. Shoot, this is, I can write with my finger. How do I erase this? Okay, so let's say that I can only take these 4 values, right? And so let's say the probability here is 0.1, the probability here is 0.1, this is 0.3, and this is 0.3, right? This is X and this is Y. Now let's assume that you saw this value of X. Nobody told you what the value of Y was, right? If you had to choose a value of Y, which value of Y would you choose? Anyone? Which value of Y would you choose? Y only takes these 2 guys, right? Which one? So no, let's call this A and let's call this B. 0.3 is the probability here. This is 0.3 is the probability. 0.1 is the probability and 0.1 is the probability, right? So which value of Y would you choose? A, because A is more likely, right? That making sense? of all the instances of X, 3/4 had Y equals A and 1/4 had Y equals B, right? And now suppose I'm having trouble with Microsoft Whiteboard because they've changed the damn thing. So suppose I had like 1 million instances of observations with exactly the same X, all right? Then of these 1 million instances, how many of them would have Y value A and how many of them would have Y value B? Can you tell me? Anyone? 75-25, right? Because P of A given X equal this X is 0.75, P of B is 0.25, right? So now here's what I will do. I'm going to make a large number of clones of this guy. I'm going to make some L clones of this guy, all right? I'm going to figure out if there's some way of moving this. So I'm going to make L clones of this guy. And each one is going to have this missing value filled in, right? So when I fill in the missing value, I would expect that L times P of the missing value, in this case A given X, are going to have the value A over here, right? And P or L times P of B given X are going to have the value B over here. That making sense? This is the missing component, this is observed. So if I just made if I made L clones of these, and imagine that these L clones were, some L from a very large collection of draws. I picked some L instances where the X values were all the observed X. Then I would expect that these many of them are going to have A in the missing value, and these many are going to have B in the missing value, correct? That makes sense? Right. And so I'd like to see more hands raised. Is that making sense? Okay, good. So here's what no. So don't restart. Okay. So here's what I'm going to do. I'm going to fill this. I'm going to make many clones of this guy. Okay. And I'm going to fill every possible value, but I'm going to make as many copies of each value as, so if I make L copies for any value M, I'm going to fill it L times P of M given O times, where O is the observed value and M is the potential missing value. So each value is going to occur L times P of M given O times in these filled in values. Did that make sense? Does it sound like English? All right. So now, here's what I did. I'm going to complete the vector by filling up the missing components with every possible value. But the number of times each value is going to fill in is going to be proportional to P of M given O, which can be computed from P of O comma M, right? And so here's what happened. I'm going to take this guy and make L clones of it, where L is a very large number, all right? And I'm going to fill in the missing components, where each missing component is the number of times it occurs is going to be proportional to P of M given O. So it's going to be it's going to occur L times P of M given O. That's what I'm going to make L copies of this guy and put in all the missing components. Similarly, for this one, I'm going to make also exactly L copies. Again, L is a very large number. And I'm going to fit in each combination of missing values in proportion to P of M given. So is this step making sense? Yes or no? Okay. Can you at least type a yes so I know that you guys are with me? Okay, thank you. And this can come from a previous estimate, right? And so now I have a completed data set. Okay. If I have a completed data set, let's just try to see what this so suppose I have each vector has been expanded to be L times, right? Now I can just say that the overall mean of the data is now the mean of this expanded data set, which has been computed by filling in these missing values, right? I've completed the data. And because every vector has been filled in, expanded by the same proportion L, I'm not over-representing anything. On the other hand, all the data are filled in, so there are no incomplete data, right? So is this making sense? Yes or no? Just say yes on this chat so I know I'm with you. Right. And so now I can compute my mean from this, correct? But then, so let xi m be, so let's consider any single vector which has xi in these components and m over here, right? How many times is it going to be observed? That is going to be observed. So if I look at it, right, that vector is going to be, I'm going to see m over here. I'm going to see this combination xm. I'm going to see this L times P of m given x times, correct? You agree? And so the contribution of x comma m to the mean is going to be this vector xm times P of m given x times L, right? Correct? Or this is not x, I should call this observed O, right? So you guys with me so far? Yes. And so I would want to sum this overall vector over all possible values of m because every O has been expanded. This is the contribution of each observed vector to the mean, right? Because again, look, over here, no, not here, look here. So each vector x has generated this box. And so from that box, the specific combination with OM has occurred these many times, right? That making sense? And this I sum over all my observations, correct? And this is going to be the sum of all of these guys. Make sense? And then I divide this by the total number of observations. But what is the total number of observations? I have the total number of vectors, but then each of them was expanded L times, correct? These L's cancel. So do you see that? So L is not the same for, no, I'm saying we don't want to over-represent any given observation. So you don't want to make more copies of some observations than others. Otherwise, you're assuming that observation occurred more times than it actually did, right? Eric? So to maintain proportionality, yeah.
Sure, but if you have one piece of missing data from one vector and 3 pieces of missing data from the next vector, won't they expand to different numbers if you fill in every combination?
So I'm saying that if L is very, very large, everything is going to get represented. But if you make this box wider than this box, you're over-representing this observation.
So you're not doing every combination, you're doing a large number of combinations?
I'm saying that every combination, if L is a large enough number, you're going to see every combination anyhow.
Okay, so in the first example, with one piece of missing data, it's probably got some duplicates, maybe quite a few duplicates.
So remember, everything is being duplicated, right? Everything is occurring these many times. Everything is occurring L times P of M given O times, right?
Sure, but if you need say 10,000 copies to fully represent 3 missing variables or something like that, you don't need 10,000 copies to fully cover the space of one missing variable.
But you're going to have
So,
duplicate in that case, right? The point is that you don't want to over-represent any one thing. Think of L as tending to infinity, always.
Okay.
Right? And so when you do that, you're going to end up with this equation over here, right? Is the sum over all missing components of the posterior probability of the missing component times the O comma M. Xi with M in the parentheses basically is O comma M. And this is, if you actually work it all out, as this goes away, right? So it's just going to be 1 over n of 4. So this term here is spurious. It's going to be 1 over n of 4, right? And so, but then if M is continuous in the limit, this summation becomes an integral. And so that's how you end up with this formula for the updated mean. Is that making sense? And do you guys see where this equation came from? Yes or no? Can I see a yes and a yeah? Right. And so the same thing. Now I can do the same thing over here. I can just expand for every completed vector. I can do x minus mean times x minus mean transpose. This combination is going to occur P of M given O times, correct? And so I'm integrating over all possible values of M. I'm summing over all observations, 1 over N. This is going to be my updated estimate for the variance. So do you guys see where this equations came from? Right? Easy, right? So that's what EM is doing. Now let's take a case of the Gaussian mixture problem. Here, we don't know which Gaussian each vector came from. Now, consider this case. So let's say I have these three. For some reason, it's not letting me use my pen, so I'm doing this with my mouse. So let's say I have these three Gaussians, Gaussian 1, Gaussian 2, right? And Gaussian 3. And now, let's say I observed this particular observation. And if this particular observation intersects here, so if I plot this, right, then let's say this height on this Gaussian is say 0.1 and or 0.2, right? And let's say this height on both Gaussians is 0.4 or proportional to 0.2 and 0.4, right? So if you got this observation, and then if you had like 1 billion of these observations, how many of them do you think were obtained because in the first step you selected the black Gaussian? 20%, right? And how many came from the purple? Yeah, 40%, and the red would be 40%, right? So that is, once again, it's going to be proportional to P of K given O. Yeah. So we're back to where we are. I'm going to expand. I'm going to ask, if I saw a very large number of these vectors, how many of these would have come from each Gaussian? Each vector, every Gaussian is theoretically capable of generating that particular observation. So if you had a very large number, some proportion K of O, K given O of those are going to come from the kth Gaussian. So I'm going to complete the data by attributing every vector, the data vector, to every Gaussian. I'm going to assume that I saw a very large number of instances, some large number L of these guys. In my example, I have 3 Gaussians. So the number of instances that of those L that came from the blue Gaussian, what is that going to be? Anyone? If I saw L instances of O, how many of them would have come from the blue Gaussian? Eric, how much would that be? P of blue given O times L, right? And P of green given O times L is going to come from the green Gaussian, P of red given O. So, and of course, the P of K given O can be obtained from the previous estimate of the model. So here's what I'm going to do. I'm going to take my data and I'm going to complete it in every possible way. So this box actually represents L clones of this O, where L is a very large number tending to infinity. And then this one represents all copies of this O that were assigned to the blue Gaussian. This one represents all copies of this O that were assigned to the green Gaussian. And this one represents all copies of this O that were assigned to the red Gaussian. So is this picture making sense? Yes or no? Okay, so beautiful, right? And now once I do this, I can just segregate out all of the blues, all of the reds, all of the greens, because now I have complete data and I can re-estimate my Gaussians, right? But let's take a look at this blue Gaussian, right? If I take a look at the blue Gaussian, I have many instances of vectors. I have vector 1. I have vector 1, which was assigned to the blue. So let's call this O1, right? I have O2, which is the second vector. I have O3, which is the third vector, right? So how many, all of these are assigned to the blue Gaussian. So this O vector, this first guy, how many copies of this one do I have assigned to the blue Gaussian? Anyone? How many copies do I have assigned to the blue Gaussian? Can you tell me? We just went through this, right? It's going to be whatever number I expanded it by times P of blue given O, correct? That's what this guy represents. Yes? Yes or no? O1. Did I lose you or is that making sense? So this absolute silence. Can someone answer? Did this make sense or do I have to go over this again? Anyone else? I just have one answer. I'd like to make sure. Yeah, right. This one's correct. So how many of these were assigned to the blue Gaussian? Of O2. Harshit, maybe you can answer that. It's going to be L times P of B given O2, right? And this one is going to be So overall, it's going to be summation. The total count is going to be L times all observations, P of B given O. This is the total count of vectors assigned to the blue Gaussian, right? But then if you want to take the average of all of these vectors, what is it? I had O1 being, I have L times P of B given O1 copies of O1, right? So the sum of all of those guys is L times P of B given O1 times O1, right? And so the sum of all of these guys is going to be the sum over all observations of the sum over all observations, L is common, of P of B given O times O, right? And so if you want the average, it's sum over O, P of B given O. The L cancels out. Correct? Is this making sense to everybody? The rest of you guys are making sense. I'm running out of time, so okay. And so, any questions? And so when you segregate these things out, you're going to get that the updated mean is the 1 over the sum of the updated mean for the kth Gaussian is the 1 over the sum over all of the sum over all the observations of the posterior probability of the kth Gaussian given the observation times the sum over all observations of the posterior probability times the observation. So you see where this formula came from? Yes or no? All right. And so also you would get the same formula for the variance. Yeah? Yes or no? Okay, perfect. And so the formula technique we came up with was that we have to initialize the means and variances and the prior probabilities of the Gaussians. We computed P of K given O using the current estimates of the parameters and then used those to update the formula parameters using this formula. But then that's the details, right? The point we wanted to bring across was this, that what we did was to complete the data by filling in the missing values in both cases. And the way we filled in the missing values, we wanted to be unbiased. So we filled in every possible plausible value for these missing terms. And the number of times they occurred was in proportion to P of M given O. This now gave us a completed data set. And then we just once we had the completed data set, we knew how to deal with the estimation problem. We estimated the parameters from the completed data set. Does that make sense? Yes or no? Right? So this is easy, right? It's not complicated at all. The math makes it look a lot more complicated than what we're really doing. But then, given this, what is the key thing we are doing over here to make the problem so tractable? Can someone tell me? What was the key thing we were doing to make the problem tractable? Anyone? We were completing the data, right? Because once you had the completed data, then estimation was trivial. It's just that completing the data depended on the current estimate of the distribution itself. So we ended up with an iterative solution where we initialize the distribution, used it to complete the data, use the completed data to re-estimate the distribution, and so on. Does that make sense? And I see some hands raised if this made sense. Okay, half a dozen people. So can you give me some other way of completing the data? Sample, right? It's sufficient to complete the data by sampling the missing values from the posterior. So all we could do was, after initializing the models, we could sort of complete each vector simply by sampling from, you don't even need to make many clones and complete each one separately. You could just complete each data point by sampling from the posterior. And now you have completed data, and from the completed data, you can re-estimate the parameters. And that too should have essentially the same effect. And just, considering every possible value is a more complete and cleaner solution, but sampling will work just fine. So the overall principle, remember this, you have some missing data or information, you initialize your model parameters, then you complete the data according to the posterior probabilities, either by implicitly considering every possible value or by explicitly completing it by sampling the posterior distribution. And then you re-estimate the model. So is everybody here with me so far? Any questions? Questions, anybody? If you have understood this, can I see some hands raised? Let's start. I'm going to stop in a couple of minutes, but I'd like to see at least half a dozen hands raised. Okay. So the key here was that you had to sample from P of M given O for this to work, right? What do you think would happen if you didn't sample from P of M given O, but you sampled from some other distribution? Would it still work? So okay, the given examples. So Eric, the given examples are, in this case, incomplete Gaussian data are a very common problem. Gaussian mixtures are a very common problem. But so maybe if you guys will let me run over for by 5 minutes, I'll sort of give you a preview into what's going to come in the next class. But before I do that, I want to give you something very surprising, right? We know that this whole completion process works if we sample exactly from P of M given O. What happens when we sample from P of M given O is that if you have some f of theta, this is your log likelihood function, then the J function is going to sort of touch exactly. So this is J theta 0, right? And so if the J exactly touches over here, the theta 0, then in maximizing J is guaranteed to maximize F as well. But then you don't need J to exactly touch it. If it comes close, it's often sufficient enough. It didn't exactly touch it, right? So what this means is that if your Q of H in the original formula was not exactly equal to P of M given H, Q of H given O, but something approximating it, then too the technique has a reasonable chance of actually giving you a continuously increasing sequence of estimates. Did that make sense, guys? Aaron, did that make sense? So what would that map onto over here? Anyone want to tell me? What would that map onto? So in which case, so where is this now going to be useful? There are many problems where P of M given O is not a tractable function. This is what we're going to encounter in the problems that we will see in the next class. So what we will do is to approximate P of M given O by some other function which is tractable but very close to P of M given O. For instance, suppose you model P of M given O using a neural network, right? So remember, going back all over here, basically we have P of M given O is just a Q of H, right? So it was just Q of P of M given O, P of H given O is just Q of H, right? The best case value of Q of H. But then if I can't actually compute P of H given O because my function is very complicated, then I can try to learn some kind of a neural network which maximizes this guy. And in that case, Q of H is going to be very close to P of M given O, but not exactly that. And then you can use that. That's why it's a variational overbound. And then you can use that to do the filling and the estimation, and things will still work. Did that answer your question, Aaron? So any other questions, guys? Yes, no. Okay. So how is this going to make life different for us? So I'm going to skip all of this tomorrow. I'm going to talk about linear Gaussian models, where I can say that there's a kind of Gaussian probability distribution function, something called factor analysis, where you assume that some Gaussian random variable has been put through a linear transform, and to it noise has been added, and that's how data are generated. This is a model for this looks like your autoencoder, except that there's some addition of noise at the output. And this is a model for, let me see, for Gaussian probability distributions. It says that the data have a roughly Gaussian distribution close to a planar surface. And the problem we began with early in the class is that of trying to generate faces. And in that case, you're going to have a problem where the data are distributed according to some distribution, but not on a linear manifold, but on a curved manifold. And so here, this box becomes a neural network. And so our generative model is that there's some nonlinear function which takes in Gaussians and generates faces. So that's our generative model. And if you do a very good job of estimating this guy, then it will indeed learn the distribution and generate faces. But to learn this guy, for each phase, you need the corresponding z, and you won't have the corresponding z. So we're going to use the trick that we just saw. That makes sense? Any questions, folks? No? Okay. So z was sure, what I just said. So over here, our example, suppose I wanted to randomly synthesize faces, correct? Then I would say that I'm going to randomly sample a point from a Gaussian distribution and put it through a nonlinear function, and it's going to generate a face. That is my generative model. And so, did that answer your question, Eric? And so what we would say is that for every training instance that we are learning our data from, that training instance was generated in this manner, that some Gaussian random variable was put through this nonlinear function and gave you the picture of, say, my face. And so if you knew the z that went into this box to give you the picture of my face, then you have the input and the output. You can just use backprop to learn the network itself, which converts random Gaussian random variables to face-like images. But all you're given are faces. You're not given the corresponding z's, and so now you have to estimate. You have to work your way back, right? So this is where the whole EM-like framework comes in. That answer your questions, Eric?
Sort of. It might be easier to talk in person at some point.
Yeah, no, but I'm going to cover this in the
next class.
Yeah.
Yep.
Yeah. All right. Okay, guys. Thank you very much. Let me stop the recording. And Aprajit, can you stop the recording?